welcome to Geometry, Section 1-5. Today's lesson is about segments and their measures. We've already talked about segments a little bit, and we know that they're a part of a line. Remember, the notation for a segment uses the two endpoints with a line over the top. Today when we talk about segments, we'll be measuring segments and learning how to determine the length of the segments. We'll also be learning about the segment addition postulate. So let's get started with segments. Chances are you've worked with segments before without even knowing it. We'll start talking about segments and their length using number lines. So this first term is going to be helpful to us when we're working with segments on number lines. A coordinate is a real number that corresponds to a point on a number line. And it's the coordinates that we use when we're trying to find the length of a segment. The length of a segment is the same thing as the distance between its endpoints. To find the distance, we take the absolute value of the difference of the coordinates of 2 points. Our last term for right now is congruent segments. Congruent is a word that you'll hear and be using a lot in geometry. It means that two things have the same shape and size. So when we're talking about congruent segments, we're talking about segments that have the exact same length. So here I have a number line, and on that number line I plotted segment AB, endpoints A and B. The coordinate of point A is 3, and the coordinate of point B is 15. So if I want to find the distance between those two endpoints, or the length of the segment, I just have to use the absolute value of the difference of those coordinates. So to find the distance between these two, I can just take 15 and subtract 3, and I get 12. Now in this case, the absolute value is not really necessary because the absolute value of 12 is just 12. But let's look at this a different way. What if I took the coordinate of A and subtracted the coordinate of B? According to the definition of distance or length, it doesn't matter which order I do these in. Hopefully now you can see why that absolute value is important. 3 minus 15 is negative 12, but when I take the absolute value, I still get that positive length that I need. And it makes sense that distance should have an absolute value in it because we can never have a negative distance. One more thing that's important to talk about with segments is their notation. When we talk about the actual segment itself, we would name it using the two endpoints with the line over the top. When we're talking about the numerical length of that segment, we don't put the line over the top, we just use the two endpoints. So AB with a line over the top means I'm talking about the actual geometric figure, segment AB. When I don't have the line over the top, I'm talking about a numerical value, in this case, 4. So now let's look at another way to measure segments. Sometimes we'll measure segments with a ruler to get their actual length. Our first ruler gives us measurements in centimeters. Remember, a centimeter ruler is divided into tenths. So this segment is 4 hash marks past 4 centimeters, so I would say that's 4.4 centimeters. Now we're going to switch to a ruler that measures in inches. On this ruler, the larger hash marks are for quarter inches. Medium-sized hash marks are for eighth inches. There are 8 of them between 2 inch marks. And then the smallest ones are for 1/16 of an inch. And it looks like the segment that I'm measuring here is in between 2 and 3 inches. So I know that my whole number part of my answer will be 2 inches. And then it's 1/16 past 3/4. If I get a common denominator, 3/4 is 12/16, and 1/16 past that would be 13/16. So this segment is 2 and 13/16 inches long. Alright, jump on back to centimeters. So on this ruler, just like the previous centimeters ruler, I have millimeters on here. Because remember, 1/10 of a centimeter is actually just a millimeter. So we're right between 2 and 3, and it looks like we're at the 7th hash mark, so that puts me at 2.7 centimeters. Our final segment will bring us back to inches. We're almost to 2 inches, but not quite there. We're 1/8 shy of that. I have 1 and 7/8. So in this lesson, we finally get to learn about that segment addition postulate. The segment addition postulate says that if I have a point B between A and C, then AB plus BC equals AC. So to talk about the segment addition postulate, first we need a segment. So let's start with segment AC, and then I have point B between them. In geometry, the word between means that the point is somewhere on the line segment that connects points A and C. So for this example, I'll put B right here. So you're probably thinking, yeah, that's pretty obvious. And that's why this is a postulate. It doesn't need any other verification because it just makes sense to us. If you're having trouble visualizing this postulate, think of a piece of string that's 18 inches long. If I cut off a 7-inch piece, then I have an 11-inch piece of string left over. That's exactly what the segment addition postulate tells us. We haven't lost any of the string. We've just broken it into two pieces that still add up to the same amount of string that we had before. You can also use the segment addition postulate to prove that there is a point between two endpoints. So if AC equals AB plus BC, then B is between A and C. So if I have my whole segment and there's a point that breaks it into two parts that still add up to the whole thing, then that point has to be on the segment between my two endpoints. So let's look at a few examples of the segment addition postulate. In this example, I have segment FH with point G between F and H. According to the segment addition postulate, FG plus GH should equal FH. I know that FG is 17, and I know that the entire segment FH is 28. So using some algebra, I can substitute those values in for the segments, and I'll have 17 plus GH equals 28. So in this case, I'm trying to solve for segment GH. Subtract 17 from both sides, and I can see that GH is 11 units long. Let's try another example of that. In this example, again I have segment FH. This time it measures 39 units. I have point G between F and H. Segment FG is 26 units long. So according to the segment addition postulate, 26, which is the length of FG, plus GH has to equal 39 units, the length of FH. Subtracting 26 from both sides will give me GH by itself on the left and 13 on the right. So GH must be 13 units long. One more example like this. This time segment FH is 43 units long, segment FG is 29, and segment GH is my variable. Then 29, which is segment FG, plus GH equals 43. If I subtract 29 from both sides, I can see that segment GH is 14 units long. Now let's look at some other types of problems that we can do with the segment addition postulate. A lot of times when we're doing problems in geometry is a very visual math. So there are a couple of different ways we can do things. Sometimes we'll be given problems like the ones we just looked at, where we'll have an actual picture and the lengths will just be written in. If we want to talk about segments and their lengths algebraically, we'll start to use a coordinate plane. So let's try this example. We'll plot the points A, which is at -2, 8, B, which is at 6, 8, C at 1, 4, and D at 1, -4. And the problem is asking me to determine whether segment AB and segment CD are congruent. Because they're either strictly horizontal or strictly vertical segments, I can just count the units. AB is 8 units long, and CD is also 8 units long. So yes, they are congruent. Algebraically, here's what this would look like. Remember from the beginning that the distance or the length of the segment is equal to the absolute value of the difference in their coordinates. Since the y coordinates are the same on points A and B, I can just take the absolute value of the difference of their x coordinates. So the absolute value of -2 minus 6 gives me the absolute value of -8, which is just 8. I can do the same thing for CD. Since their x values are both the same, I can just subtract their y values and then take the absolute value of that. So 4 minus -4, when I add the opposite, I get the absolute value of +8, which of course is just 8. Let's try another example of that. We'll plot the points J at -1, 8, K at 1, 8, L at 1, 6, and M at 1, -3. Now we want to check and see if segments JK and LM are congruent. Just looking at these, I can see that they're obviously not the same size. But let's look at what would happen algebraically. For segment LM, the x coordinates are the same, so I'll just subtract the y coordinates and then take the absolute value of that difference. So for LM, I have the absolute value of 6 minus -3. Add the opposite, and I'll be taking the absolute value of 9, which is just 9. Now I need to find the length of segment JK, so I'll take the absolute value of the difference in their x coordinates since the y coordinates are the same. So here we'll take the absolute value of -1 minus 1, which is just the absolute value of -2 or 2. We can see that those aren't congruent. And just for fun, I'll toss in a little tidbit from later on in our course. This symbol, the equal sign with the little squiggle on top, means congruent. So you can start your abbreviations already. Practice that symbol, you'll be using it a lot in this course. Alright, we have one more set of problems to solve. In these problems, I'm not given a picture. When I'm doing these problems, I start by reading the problem, and my next step is always to draw a diagram that represents the problem. So for our first example, point S is between R and T on segment RT. So I'll start by sketching segment RT and putting point S somewhere between R and T. The problem is asking me to use the given information to write an equation in terms of x, and then solve that equation to find the length of segment RS and segment ST. So it tells me in my problem that segment RS equals 6x minus 8, and segment ST equals 3x minus 11. So I'll add that information to my diagram. And then it also tells me that the entire thing, segment RT, is 71. The segment addition postulate tells me that if I add those two smaller segments together, RS and ST, it has to equal the length of the whole segment. So I can take 6x minus 8 and add that to 3x minus 11. Combining like terms will give me 9x minus 19 equals 71. Add 19 to both sides, and I'll have 9x equals 90. Dividing by 9 will give me my answer, x equals 10. Be careful with your geometry problems, because a lot of times they aren't just asking you to find the value of the variable, they're asking for lengths of specific segments. So now we have to go back and determine the length of segments RS and ST. So if I substitute 10 in for x, 6 times 10 minus 8 gives me 52 for the length of segment RS. 3 times 10 minus 11 gives me 19 for the length of segment ST. One of the nicest things about geometry is that you always have a lot of different opportunities to check your work. So since I know that RS and ST together have to equal 71, I can check it by adding 52 and 19, and I get 71, so I know I got the right answer. Let's try another problem like this. It starts off the same way, where we have segment RT with S in between. This time, segment RS is 5x minus 7. Segment ST is 4x minus 14. Altogether, segment RT is 60. Using the segment addition postulate, I can add RS and ST and set it equal to RT. So segment RS was 5x minus 7 plus segment ST, which was 4x minus 14, equals 60. When I combine like terms on this one, I get 9x minus 21 equals 60. Adding 21 to both sides will give me 9x equals 81. Divide by 9 on both sides, and I get my answer, x is 9. Substitution again to figure out the length of those actual segments. For segment RS, 5 times 9 is 45, and when I subtract 7, I get 38. For segment ST, 4 times 9 is 36, and when I subtract 14, I get 22. So 38 plus 22 should give me 60, and it does. One more problem like this, just to make sure you've got it. So again, we have segment RT with S between. Segment RS is 3x plus 11. Segment ST is 5x plus 13. So when I add those two together, I should get segment RT. Forgot to write that on there, but we'll sneak that in. Segment RT in this problem was 120. Here's what the segment addition postulate would give me. 3x plus 11 plus 5x plus 13 equals 120. Combining like terms gives me 8x plus 24 equals 120. Subtract 24 from both sides, and I get 8x equals 96. divide by 8 and I can see that x equals 12. Then using substitution, I can get those actual lengths. 3 times 12 is 36, and when I add 11, I get 47. For segment ST, 5 times 12 is 60. When I add 13, I get 73. And adding and 73 together gives me 190. That's it for lesson 1.5. Remember, you can always go back in the video and review anything that you weren't sure about or anything that you might have needed a second look at. Thanks for joining me, and happy hypothesizing.